When we were whiteboarding yesterday, we were coming up with one equation. It was one of the very last questions that we did, and I just wanted to be able to use that equation today. So let me just do a little quick review, and then you're going to do a few practice problems. And basically what I have here is I have a velocity time graph. I've already graphed it. You can tell that as time goes on, velocity gets bigger and bigger and bigger. You know that the velocity is getting bigger because you can see it. You also know that it's speeding up because you can look at that VT graph and you can see that it's going farther and farther and farther away from stopping. So I can tell a few things. First of all, I know it's going a positive direction. That means that I would have a positive velocity. I know that because it's on the top half of the VT. I know that it speeds up from what I've just already said. And I know that I can calculate what the slope of that line is. So m represents the slope, which would be simply rise over run. And if I pick 2 points on my graph, I'm going to pick beginning and end. My rise is 6 centimeters per second, not 8. Notice where it starts. And then my run is 3 seconds. And I get 2 centimeters per second per second. Now, if you know that 2 centimeters per second is the slope, and the slope represents acceleration. What that tells me for every second I speed up by 2 centimeters per second. Now, we already talked a little bit about this when we whiteboarded, but I just want to recap it again. Thank you, math, for being generic. We can use y equals mx plus b for anything that's linear. And we know that in this equation, we fill in the 2 things we know. We know the slope and we know the y-intercept. So in this case, if you were in math, you would write it like this. And my y-intercept in this case is 2. It happens to be the same number as my slope in this one. However, if I want to take that and I want to turn it into physics language, I simply want to call things what they are. So I'm just going to bring down my 2. And my x is generic for whatever's on the x-axis. In this case, it's my time. And we know we abbreviate our time as delta t. Our 2 is our slope, which is our acceleration, and that just comes down. And then my y equals. My y equals is what's on the y-axis. In this case, it's velocity. However, it's not the initial velocity, it is the final velocity. This should look familiar because we've done something similar to this, except in an XF equals equation where it was a position time graph. Now, finally, the last thing I want to do is take this and say, all right, if we have a constant acceleration, that means it's speeding up or slowing down by the same amount, then we can always use the same equation. So in the back of your lab notebooks, you want to write this, and it's VF, which we've just seen up above, is equal to the slope of the line, which in this graph is acceleration, delta t, plus VI. Now, VI stands for initial velocity. VF stands for final velocity. And so essentially what we have here is this equation allows us to figure out how fast something will be after a certain amount of time. If, say, we want to know after 300 seconds, not just 3. Now, if I can tell from the graph, that's fine. But if I have to do a calculation, this is when I would need it. So, if you take a look at the example here at the bottom, I'm going to do one example. My rules for word problems have always been the same. Always show all your work, show your units, show your givens. So I have got a bear spies some honey, takes off from rest. He speeds up at a rate of 200 meters per second, 2 meters per second, and he goes for 4 seconds. We want to know how fast it's going to be when he reaches the honey. So that means that we're solving for our final velocity. So that means somewhere in the problem there's an acceleration, somewhere in the problem there's a delta t, somewhere in the problem there's a VI, and I'm writing my given over to the side. My acceleration is 2 meters per second. My time is 4 seconds. And my VI, it says from rest, is going to be 0 meters per second. Now pay attention. If I don't mention a specific VI, we assume it's 0 unless otherwise mentioned. Now, next step is just simply write the equation. VF equals A delta T plus VI. There's no doubt in my mind that you all can do the math part of it. It's the units that many people struggle with. So let me just model one. So I take my acceleration, which is 2 meters per second. I'm writing it this way on purpose. Delta t is 4 seconds plus 0 meters per second. So that really is out of the equation at this point. The 0 is not going to matter. So 2 times 4, no doubt you can do the math on that. What I'm going to do is come back and take a look at the units. There's 2 ways you can figure out the unit. The first way is you know that it's got to be a velocity unit, so it has to be meters per second because that's what makes sense. The second way is to just simply look at how your units will cancel. I have a seconds on top, and that will cancel with the seconds on bottom, leaving meters per second behind. And then just circle your answer, and you're good to go. You have some example problems in front of you. Go ahead and start working on those now. Please show your work, show your units, just like I've modeled.